Let's get some practice drawing Newman projections. Our goal is to look down the carbon-2, carbon-3 bond for this compound, and in part A, our goal is to draw the most stable conformation. So let's number our carbons. This carbon we could say is number 1, this carbon is number 2, this carbon is number 3, and this carbon is number 4. If we're going to look down the C2-C3 bond, that's this bond right here. So we're going to put our eye along this axis. If I draw this out right here, we're going to put our eye right here, and we're going to stare down the carbon-2, carbon-3 bond, and we're going to draw what we see. Our goal is to find the most stable conformation, and we know from earlier videos that would be a staggered conformation. So we'll draw one staggered conformation, and then we'll draw the rest, and then we'll pick which one is the lowest energy, which one is the most stable. So here's carbon 1, and then we have carbon 2 with the hydrogen coming out at us and a methyl group going away from us in space. Attached to carbon 3, we have a methyl group coming out at us in space and a hydrogen going away from us in space. And then we have carbon 4. Our job is to stare down the carbon C2-C3 bond and draw our Newman projection. So if I rotate it, so we're staring down that C2-C3 bond, we can see a Newman projection. We can see a staggered conformation for our compound. To get another staggered conformation, I could rotate the front carbon and keep the back carbon stationary, and that gives us another staggered conformation. And I could do it again. I could rotate the front carbon to get another possible staggered conformation. In the video, we stared down our C2-C3 bond. So this bond right here, we put our eye here, and we looked at the possible staggered conformations for our compound. It's important to be able to draw the Newman projections without using a model set. So let's go ahead and do that. So if we're staring at carbon 2, so this is carbon 2 right here, and our Newman projection, that's represented by a point. So I draw a point here. And then we'd have a hydrogen going up and to the right. So if your eye is right here, your hydrogen goes up and to the right from this perspective. So we have a hydrogen going up and to the right. We have a methyl group going up and to the left. So a CH3 up and to the left. And then finally we have another methyl group going straight down. So a CH3 going down. For carbon 3, remember carbon 3 is this one right here, you can't see carbon 3 if your eye is right here. Carbon 2 is in the way. But in our Newman projection, we represent that with a circle. So this circle represents carbon 3. And what's attached to carbon 3? There's a methyl group going straight up. So again, if your eye is here, this methyl group is up. So we have a CH3 going up. We have another CH3 going down and to the right. So this is going down and to the right. And then we have a hydrogen going down and to the left. So here is our Newman projection for a staggered conformation. Next, we rotated the front carbon and held the back carbon stationary to get another staggered conformation. So let's go ahead and do that. Let's hold the back carbon stationary. We're going to take this methyl group and we're going to rotate it all the way over to this position. If we do that, then this hydrogen rotates all the way over to this position, and finally this methyl group would rotate over to this position. The back carbon stationary, so let's go ahead and draw the back carbon, a circle, and the CH3 is going to stay in the same spot. This CH3 stays in the same spot, and this hydrogen stays in the same spot. So we rotated the front carbon. It doesn't really matter if you rotate the front or the back carbon, but let's go ahead and draw in our groups here on our front carbon. So here's C2, and we moved the methyl group in magenta over to here. So let me go ahead and draw in that methyl group. That methyl group moved over to here. Next, the hydrogen in blue moved down here. So I can draw the hydrogen in blue here on my Newman projection. And then finally, the methyl group over here in red moved over to this position. So the methyl group in red moved over to here. And now we have another staggered conformation. For our last staggered conformation, we're going to do the same thing. We're going to take the methyl group in magenta, rotate it over to here, And then that would cause the hydrogen right here to rotate over to this position, and the methyl group in red to rotate over to this position. So we keep the back carbon stationary, so we draw that in as a circle. Again, we put in our CH3, we put in our CH3, we put in our hydrogen, those aren't moving. And the methyl group in magenta is now down. So this is the methyl group in magenta. The hydrogen moved over to this position, and finally the methyl group in red moved over to this position. So now we have our staggered conformations. And we can double check ourselves by comparing these Newman projections to what we saw in the video. So here are the staggered conformations. These are stills from the video, and you can see they match the Newman projections that we drew. Finally, we need to choose the most stable out of these three. So what is the most stable conformation? Well, we know that when we have this situation, let me go ahead and use blue for this. So when we have a methyl group, and methyl group here, right, that are 60 degrees apart, this is a gauche interaction. So we have a methyl-methyl gauche interaction. And from the video on butane, conformations on butane, we saw that a gauche interaction has 3.8 kilojoules per mole as an energy cost. So we have 3.8 kilojoules per mole for this gauche interaction. And we have another gauche interaction here, so another 3.8 kilojoules per mole, and another gauche interaction. So there are three gauche interactions for this conformation, for a total of 11.4. So the total would be 11.4 kilojoules per mole as an energy cost. So 3.8 times 3. What about this conformation? Well, here's a gauche interaction, here's a gauche interaction, and here's a gauche interaction. So again, we have three gauche interactions. So for this conformation, the total energy cost is also 11.4 kilojoules per mole. What about this conformation, our first one? Well, here's a gauche interaction, so that's 3.8 kilojoules per mole, and here's a gauche interaction. Well, we have only two for this conformation, so only two gauche interactions. That would be a total of 7.6 kilojoules per mole, which is the lowest energy. So this is the most stable conformation. In part B, our goal is to draw the least stable conformation. And we know that the least stable conformation is the one that's the highest in energy. So let's go to the video where I take the model set and I go from the staggered conformation to an eclipsed conformation, and then we look at all the possible eclipsed conformations. One of them is going to be the least stable. Here we start with our staggered conformation, and if I rotate it a little bit, we get an eclipsed conformation. I left it a little bit off so you could still see the back bonds. I rotate again and get another eclipsed conformation. Now for this one, if I turn it to the side, you can see these methyl groups are really close together in space, and so that steric hindrance would destabilize this conformation. So if we go back to the eclipsed conformation, we rotate again, we get to the final eclipsed conformation. Here are the pictures of the eclipsed conformations from the video, and our goal is to pick the least stable, but just for practice, let's try drawing all of them as Newman projections. So we'll start with the one on the left here, and we're staring at C2, so that's C2, which we represent by a point, and then C2 has a methyl group going up, and I drew it a little bit to the right just so we can see what's going on behind it. And then we have a hydrogen going down and to the right, so there's a hydrogen bonded to C2 going down and to the right, and then over here is another methyl group, so to the left is a CH3. For the back carbon, even though we can't see it, we represent it with a circle. So the back carbon right there, which is C3. What's bonded to C3? Let me use a different color, and hopefully you can see there's a methyl group back here bonded to C3. So let's draw that in red. And then there's another methyl group over here. So this is a methyl group. I'll draw that one in, a CH3. And then we have a hydrogen down here. So here is the hydrogen. So that would be the Newman projection for this eclipsed conformation. Let's move on to the next picture. So this eclipsed conformation. So we're staring at C2, so that's our dot here. And then we can see there's a methyl group going up and to the right, so a little bit to the right. So there's a CH3 going that way. There's a CH3 going down, so this CH3 going down, and then we have a hydrogen going to the left. So hydrogen going to the left here. And then in the back, right, we have our carbon 3. And we held the back carbon stationary in the video, so there's no change. You can see there is a methyl group straight up here in the back, so CH3. And then there's a methyl group going to the right back here, so a CH3. And then there's a hydrogen going to the left, so there's a hydrogen here. So here's the Newman projection for this conformation. And to go from the one on the left to the one on the right, we rotated the front carbon. So let me go ahead and show which carbon is which. So if you took this carbon and rotate this methyl group, I should say, and rotated it over here, that methyl group in magenta becomes this methyl group. The hydrogen right here in blue gets rotated over to this position, so that's this hydrogen. And then finally, this methyl group right here in green would get rotated over to this position, so that's this methyl group. All right, for our last eclipsed conformation over here, we're staring at C2, so let's draw that C2 here. We have a hydrogen going up a little bit to the right. We have a methyl group going down, so we draw in that CH3. And then we have a methyl group going in this direction, so a CH3 here. We'll draw in the back carbon, so there is C3. Again, we didn't change anything, so again, there's a methyl group going straight up, so CH3, a methyl group going this way, and then, so that one right here, and then a hydrogen going this way. So here's our hydrogen. If we show going from this conformation to this conformation, again, we'll start with the one in magenta. So this one in magenta was moved over to here, so that's this CH3. The hydrogen in blue was rotated over to this position, so that's this hydrogen. And finally, the methyl group in green was rotated over to here. And so now we have our eclipsed conformations, and let's analyze them and determine which one is the highest in energy. If we start with our first Newman projection, so this one right here, we have a methyl group eclipsing a hydrogen. And we know from earlier videos, that's an energy cost of 6 kilojoules per mole. Here we have another situation with a hydrogen and a methyl group eclipsing each other, so that's 6 kilojoules per mole. Finally, a methyl group eclipsing a methyl group, which we know is 11 kilojoules per mole. So that's a total of 23 kilojoules per mole, the energy cost for this eclipsed conformation. So let me go ahead and write that here. That's 23 kilojoules per mole. Let's go to the one on the right next, because you can see it's the same thing. We have a methyl group eclipsing a hydrogen, so that's 6. We have another situation with a hydrogen and a methyl group eclipsing each other, so that's 6. And we have a methyl group eclipsing a methyl group, so that's 11. So this one's also 23 kilojoules per mole. If we look at the one in the middle, it's a little bit different. We have a pair of hydrogens eclipsing each other. We've already seen that's 4 kilojoules per mole, so that's 4 here. We have a methyl group eclipsing a methyl, which is 11, and then we have another methyl group eclipsing a methyl, which is another 11. So what is 11 plus 11 plus 4? That's a total of 26 kilojoules per mole. So this is the highest in energy. This is the least stable conformation, the one where the methyl groups are the closest together in space, because these relatively bulky methyl groups, these destabilize this conformation. So you want to get the bulky groups as far away from each other as you possibly can.